All right. Roger, can you see that okay?
It's just fine.
All right. Well, as Roger said, I'm going to talk a little bit about some of the observations that people made during the Titan occultation last month. Titan is a very interesting object simply because it has an atmosphere, as you can see in the picture here. This is a picture, a NASA picture from Cassini, or NASA ESA picture. The surface you can see because I used like 4 different IR wavelengths, so you can see a little surface detail, and then these some UV wavelengths so that you can see the haze layer around the moon, which has a very significant atmosphere. So when we have an occultation, you get some interesting phenomenon you normally don't get whenever you have like an airless asteroid going in front of a star. So what I'm planning on doing here, I'm going to talk one chart, just what is Titan, go into a little bit of the atmospheric phenomenon that we can see during an occultation. And I am by no means an expert on planetary atmospheres, atmosphere of Titan. So I pretty much have a Wikipedia knowledge and really not even that much. So, take everything I take with a little bit of a grain of salt. I'm learning this stuff and trying to figure out what's going on. And if you have something you want to correct me or something, feel free to pipe in. But after I do that, go through a little bit about what can happen. I'll talk a little bit about the event, and I finally will show the results at the end so you can see what everybody did. There's quite a bit of results. So Titan, largest moon of Saturn, and it is large, 40% of the size of Earth, the diameter is. And so it's pretty major moon. One thing you'll read a lot when you go online, it says it's the only moon in the solar system with a significant atmosphere. And it probably depends on what you consider significant as to whether or not that's true. There's actually 4 moons in the solar system that have an atmosphere that the Planetary Society, on the website they had, said that the density is high enough that you can have collisions between molecules in the atmosphere. All the other ones, it's so rarefied, atom bounces off the surface, it will not hit another atmospheric molecule. It'll just go as if they don't exist. It'd be totally rarefied. The 4 that do have enough atmosphere for that, those collisions occur, are Titan, which its sea level pressure is about 40 or 50% higher than that, the sea level on Earth. So it's really got a significant atmosphere. It's also into mostly like 95% like Earth is. The next one's Triton. It's much more rarefied, only 1/20,000th of the pressure on Earth. But it's significant because if you have occultations of Titan, or Triton, you can also see effects of the atmosphere. That's been seen in the past. And so I would consider that to be a significant atmosphere since it's something I can play with. The other 2 they had on the list was Io, only 1/200 millionth of Earth. I don't know if you have any chance of seeing anything when there's an occultation, unless maybe one of these plumes is erupting right at that point and you have enough chords, maybe you can detect a little plume on there, but I don't know if that's even possible. I don't know if that's ever happened. And finally, Callisto, 1/40 billionth of Earth's pressure. And that's really low. In fact, it's, just fairly recently, they said, yeah, it looks like it really can have collisions and we should be included in the list. We have at least 2 that for occultations have a significant atmosphere, which is better than just Titan. One other thing about Titan's atmosphere is Titan, since it is smaller than Earth, it's got less gravity. And that means that the atmosphere is extended to a farther distance from the moon than Earth's atmosphere is, which is good for occultations because we get a nice long trip through the atmosphere that we can record. So what can the atmosphere do to our occultations? This is a picture I just blatantly stole from the reference you can see at the bottom of the page. This shows kind of 3 different effects you can see. The blue circle or half circle is, in our case, Titan. The dotted line going around it is the upper limits of the atmosphere. It's really very nebulous, but we'll say there's an end to the atmosphere out there. And then the horizontal or pretty much horizontal arrows are showing light coming from a star. The star is well off to our left, out at infinity basically, and then we're observing from Earth way off to the right in this picture. The upper left-hand picture shows one type of phenomenon you can get. It's a extinction or attenuation. Basically, you can see the light rays, of course, that miss the atmosphere completely or unattenuated by it. As you get deeper and deeper in the atmosphere, the density is rising exponentially. And so you start seeing effects, scattering of the photons by the atmospheric molecules or absorption of the photons. And so you start getting a dip. It's wavelength dependent, like on Earth, we get the blue sky because of the scattering by the nitrogen and I guess oxygen molecules. But that's one of the first effects. You'll see a lot of attenuation close to the surface and not so much out far from it. Another type of extinction they don't talk about here is you can also have haze in the atmosphere, and Titan has a lot of haze. So that's just going to block the light. You can also have clouds, and that will also cause extinction. And those won't necessarily be over the entire surface, although Titan has a very solid haze layer. So it's fairly constant around the surface. I'll show some pictures of that in a moment. In the upper right, the second thing we've got is effects of refraction. In this case, you have a density gradient going from the surface out to the edge of the atmosphere. And since you have that gradient, as light goes through it, it bends. And in this case, it bends the starlight closer to the center of the moon. And you can kind of see the angle it does it in a little plot that they have over there at the right. Now the biggest effect is going to be due to that big density gradient across the atmosphere, but you can also have local density gradients due to like temperature inversions. Anything where there's a variation in temperature, you'll get a variation in density, and that can cause these light rays to jump all over the place, and they won't be nice, almost parallel lines like you see here. The final thing, they kind of combined it all in the picture at the bottom. And in this case, they're showing the little blue circle, which is Earth flying by in our case. And you can see the refraction, at least in this picture. And over on the far right, they have a picture of the light curve that results. And they've got laying on its side. The left side of the plot is zero flux. The right side of the plot is, fully illuminated star. What happens is the Earth starts off at the bottom. There's outside the atmosphere, there's absolutely no effect. Then you start getting into the refracted region and also the region where extinction is coming from the thicker atmosphere. You start seeing the light levels drop, a very smooth drop as the density increases. But then, even as you get down to the bottom, it's not a nice sharp edge because the star can actually be behind Titan, and the refraction will curve the light around it. So it never totally disappears. I'll be showing that in a minute. Never totally disappears. So it's a very gradual change to become a flat value at the bottom of the curve. And then if you're really close to the center line of the event, you can have what's called a central flash. And that's where the star is almost centered directly behind Titan, and light curves through this atmosphere, and it's probably a ring of light that then comes down to a point where you are, and you see a big increase in brightness, even though it's completely behind Titan. We didn't really have that for this event. Nobody was close enough to the center, but I will talk about that a little bit more. But those are the three big phenomenon: extinction, attenuation, refraction effects, and then the central flash. So these are some actual pictures of Titan from the NASA JPL Space Science Institute, showing some of these effects I was talking about. And this first page is just talking about extinction. Upper left-hand picture, we have a picture of some haze layers. These were all taken by Cassini, by the way, obviously. But anyway, the haze layers, hopefully you can see on your screen that the purple is the haze, and there's gaps in between, and of course a star going through there. You would expect it to be changing in intensity as it goes. Now this picture was taken in ultraviolet. It probably looks very different in the visible light that we're really recording in, but the effects are going to be there. Excuse me. The middle picture kind of shows that Titan's atmosphere is not just a perfect onion with perfect layers that are all the same thickness. In this case, there's an increase in haze near the pole. This was, I think, when Cassini was there, it was like the northern winter, I believe, and this polar cap will appear in the atmosphere. And so that's going to cause different effects depending on where your car happens to go through the atmosphere. It does have some clouds. This is an extremely enhanced picture in the upper right-hand corner of methane clouds. I don't know how high these are. These may be so close to the surface that we don't really encounter them in an occultation, but I could see something like this still having an effect on keep making our light curve where it's not a nice smooth curve. Finally, in the lower right, I should have included just a picture of Titan the way we see it with the telescope, but it's just a kind of orangey, fuzzy ball. It's got so much haze, it's just a featureless orb out there. But whenever they use really play with the levels in post-processing, you can see that there's some banding in that atmosphere. And so again, during an occultation, those changes in density of the haze can cause effects. You also see a couple of dust donuts there. I'm glad I'm not the only one that has those. Now that's the extinction part. For refraction, I didn't really have any great pictures, but I did find this data from the Huygens probe as it descended down to Titan's surface. On the left, we have density on the x-axis, altitude on the y-axis, and then on the right, temperatures on the x, but again, altitude on the y-axis, two different scales on the altitude. As you can see on the left, got the big density gradient I was talking about, very high densities close to the surface. In fact, that's much, much higher than Earth. Earth is around 1.25 kilogram per cubic meter at sea level. Titan is much higher because it's got that extra 50% of pressure. It's also very cold, and so it's very dense down there. Then that falls off exponentially by 100, 120 kilometers. It's almost to zero. In fact, that's as high as the probe took data. They didn't take it above that. That's why this chart doesn't keep going. So that's going to be one of the big refraction effects. The other one I said is due to temperature variations in the atmosphere causing density variations. And that's shown on the right with the temperature. It goes all the way up to 1,400 kilometers. And you can see that the temperature is not constant. So everywhere it zigs, the density is going to be zigging. Famously, there's around 500 kilometers. There's usually a temperature inversion that is generally visible in occultation data. In fact, I saw a paper by Bruno Siccardi where he said that around 525 kilometers is the extent of the distance from the planet where the atmosphere will affect an occultation. So you'd expect to see some effects of that around 500 kilometers. Also, I should point out that point supposedly moves at different seasons to go down to 380 or something like that. But in general, you're going to have effects like these in the atmosphere. So what does this really look like? And y'all probably all seen this video, but it's so cool, I had to include it. And I can't stop it, but I'll restart it a few times. This was a video taken by the Polymer 200-inch telescope in 2001. I was glad to see something from Polymer. You hear about Hubble and Webb, but I still like Polymer. What you see, this Titan in the middle, very well resolved, much more resolved than my telescope does. And it was a double star that accompanied it. And so you see the two stars drifting through the field of view. Now, whenever it starts over here in a second, you'll see as it enters the atmosphere, you see flickering of the star. And if you look very closely, you can see a little refracted image of it going around the top of Titan. And then it goes flickering and comes off the other side. There's also a refracted image on the opposite side. Like in this case, the big one's going to be on the bottom. You see it sweeping around, and the faint one sweeping around the top if the screen's good enough. If your image isn't good enough, I got the link down there, and hopefully you can read that or get a copy of this and see where that is. David Dunham has it on the occultations.org website. But very interesting phenomenon. So you're seeing the flickering through the atmosphere due to those density gradients and also probably variations in the haze layer. And then you see the refraction. Basically, you always see the star as the whole time it's behind Titan because of refraction. Unfortunately, as you can see in the left-hand picture, Polymers was halfway in between the two stars, so it wasn't on the center line of either one, so they did not get a central flash. I assume if they had, we'd had like a ring of light that appeared at that time. I guess you really can't have everything. So that's what it would really look like if you had a really nice telescope, and it kind of shows the phenomenon I was talking about. So that's enough background. Yeah, I'm already 13 minutes into some background. But so now I would briefly describe the event. Like we said, it's July 9th. It was about 4:20 in the morning here. So it's one of those you have to wake up for. Titan, its magnitude is about 8.5, so it's quite bright, which is very nice. Unfortunately, the star was about the same brightness, magnitude 8.7, so there wasn't a whole lot of magnitude drop, only 0.66. And that led to noisy videos, low signal to noise ratio, which makes analyzing this data a little bit tough. I don't envy the Lucky Star people who are going to be doing all this, but I'm sure they can do a much better job than I did. The event, the maximum duration, I've got in quotes here, 326.6 seconds. I think that would be if Titan didn't have an atmosphere, that would have been the maximum. But something with an atmosphere, that's kind of a nebulous number. But it was, 5 minutes that you're able to see something happening. So the picture up in the right-hand corner is another one David Dunham posted several times, a link to that during the event. He gave us a very good description of how to see this event. But it shows Saturn with the little pluses or several of the moons, and then the black dot over on the left-hand side is the star. You know, at a magnitude 8.7 star looks pretty big. It's a scale, and the way they do magnitude scales. Titan's a little plus on top of it. You may not be able to see on your screen. That's where the occultation was going to occur, so it was well away from the planet, which was a plus. The bottom picture shows the field of view from an 8-inch SCT, like what I've got. Unfortunately, there weren't any stars that were really close in brightness to Titan. That'd be very good, because in this case, Lucky Star is interested in photometry. They want to see the variation in brightness over time, unlike a normal occultation where it's just pretty much on off is the main thing we care about. So you'd want a really good comparison star. Most of them are much dimmer, and I know I use some of these to try to adjust people's light curves that they sent me to take out clouds and that kind of stuff, and these dim stars just don't work well for that at all. I did manage to get star A in my video, but unfortunately it was saturated because it was so much brighter than Titan was. The shadow path, this is the typical occult plot. It was, you know, Titan's a big moon, so it gives you a big shadow on the Earth. And this is the shadow of just the moon itself, not including the atmosphere. It covers most of North America, all of Central America, and a little bit of South America. Unfortunately, all the observers were just in the US and Canada, and one from Russia I'll mention here in a minute. I think that's all I was going to say at this point on that. But it was a big shadow path, and a lot of us got to see it. Oh, another thing I was going to mention, of course, we have an atmosphere, which means the actual area where you can see the effects of occultation extend quite a distance outside of this. And you'll see we had multiple observers who are well outside this path, but they still got to see the event. The path had a very low uncertainty because they know pretty well where Titan is, but even then they were out 3 or 4 sigma, 5 sigma, and they were able to see the event. So here's the observers, as best I can tell. There's a whole bunch of different sources. IOTA didn't really gather all the data to do their normal analysis because this is so different from everything else. It's really going to be a Lucky Star analysis. With piecing together IOTA stuff and Lucky Star stuff and some random emails, I think this is pretty much a comprehensive list of people who at least wanted to try to do the event. 45 people. Not everyone was successful. You know, some people had clouds and who knows what else happened, but I listed them all anyway because they tried. 36 people, though, as far as I can tell, had successes and actually recorded the occultation. 39 of those from the USA, 2 in Canada, like I said, 1 in Russia. That doesn't add up to 45, but I don't know where everybody lived that had a success. I can't really tell you that for sure. The red stuff, like I had 3 EVs on there. Those are people with EV scopes. They had at least 3 people were able to record it. That was kind of interesting. And then R is the remote one of Philip Romanov, who was in Russia, but he really wanted to participate in this. And so he basically used a remote telescope in New Mexico. And I'm going to briefly talk about that because I thought it was interesting. He uses this telescope. It's in the itelescope.net system. It's located in New Mexico. Celestron Rasa 11-inch. It was free for him to use. He only gets 30 minutes to use it, you know, once every 18 hours. But so he timed that right. Somebody got done and he was able to record the event. He had to take long exposures. There were actually 10-second exposures. I used a 60th of a second exposure. But part of that was because it was a color camera. He had some control over that. So he ended up using the green channel of that for his data reduction. And he also had 40 seconds between his exposures as opposed to the 60th of a second like I used. He had to do that because it's a large sensor. It doesn't download that quickly. And it's also the first time he said he'd used the scope. And so he found out there was ways to speed it up. He can at least get 8 seconds. It sounds like he can get it quicker. So I'm sure he can improve that in the future. And even though this is a very low rate and not that useful for the atmospheric phenomena, this could be very useful for some of these high priority things like trans-Neptunian objects, things that we have, they're large, but we have no idea where they are or whether or not they've got a moon. And so hopefully he'll be able to use this kind of thing in the future to participate. So that's kind of everything about the event and all the people that were watching the thing, trying to record it. And so now I want to get into the results. And before I actually show any of the people's light curves, one thing I've got to say is, I wanted to compare light curves between people, see if everybody's seeing the same atmospheric phenomenon, or people that are close together and all that, which means I had to line up the data in time and space. We had predictions of where they were, but of course, that's never exactly right. The issue is, like for normal asteroid occultation, you can see a very sharp disappearance, a very sharp reappearance, and you run it through IOTA or whatever, and it will tell you what the mid time is, and you can line up everybody's mid times, and you'll get a nice outline of the asteroid, and you're done. In this case, the DNR times are poorly defined because of that atmosphere. It makes that S-shaped curve as it comes in. And as we saw when people were sending in their preliminary light curves, that makes it hard to line things up. There are codes. I know Tony George is saying IOTA does a decent job of fitting those slopes, but I didn't really want to do that. So what I ended up doing was just simply taking the predictions, the predicted event time and the predicted chord offset. And I said, those are exact. Those are perfect. That's how I'm going to line everybody together. And that's pretty good because even if everything shifted by 20 seconds, everybody should be shifted by 20 seconds. So the deltas between people should work out. Same thing with the chord offset. If it's really was 30 kilometers south of where people thought the prediction said it would be, well, everybody's off by 30 kilometers. So you can still look at the difference between them. That said, there were some times I needed to try to adjust that out for some of the plots I was making. So I did do a little bit of that. One thing, I took the absolute values of the times, and so I plotted the light curve versus time, but absolute values, so the DNR fell on top of each other. And then I could see how much delta everybody needed. Everybody should have needed the same delta to make DNR fall on top of each other. So I did that. That worked pretty well. And then for the chord offset, what I did there was plotted versus distance instead of time on the x-axis. And of course, we had distance, the offset distance on the y-axis. And I did that until I shifted the chord offset until I got a circle. That took a little, a circle centered on where I knew the moon was. And that worked fairly well. I think I missed it a little bit, but that allowed me to get things much closer than I can do by looking at these fuzzy D's and R's. So here is almost everybody's card that I received, or light curve that I received. And I've ordered this in 4 columns, starting in the upper left. Peter Ceravolo, he was the person farthest from the center line of the event. He was well outside the predicted ground track, but he just grazed the upper edge of the atmosphere. If you come down to Bill Hanna and keep going down, you get deeper and deeper into the atmosphere. And somewhere, I think, around Ted Swift, somewhere down in there, you start hitting the planet itself. Of course, where the star is, due to refraction, it's going to be shifted. I don't know how you really define who was behind the moon or not, but it's somewhere in there that those effects really, where you really start getting full occultation. You continue down each column across, you can see Philip Romanov's had the 40-second resolution, but still got decent light levels. And you finally come down to the lower right-hand corner with, excuse me, with Andy Howell. He was the person closest to the moon center that I had data for. A couple of the EV scope guys were even closer. So they may have gotten something interesting, but I didn't have their data. Now, what started this whole impetus to do a talk on the Titan observations was some spikes you see, and I'm going to use mine as an example. It's over in the lower right-hand corner, I'm the second from the bottom, Stuart. You can see, of course, the D and R events. You also see it at both of those are spikes. Quite a few spikes at the D, and I've got one big spike at the R, where the light got much brighter than even the star was when it wasn't occulted. And that's probably due to refraction effects in the atmosphere, focusing the beam as it goes through those different haze layers or density layers, causing the brightness for a while to be brighter than what it would have been otherwise. And so I sent that into the group, and other people said, "Oh, I got the same thing." Is if you look through all of these, just go up and down the columns, you'll see a lot of people got spikes at the D or at the R or both. Some people didn't get the D or the R and have different cloud problems. Interesting seeing all the issues people have, but was very interesting to see that. And so I wanted to see if I could pull a little bit more data out of that in comparison some of the results and see what we were seeing in the atmosphere of Titan, to see if we were seeing those effects that I was talking about earlier. So we'll talk about a few of these in detail, not a whole lot of them, because after a while it's like, well, this one has a spike here and that one has a spike there, and it gets a little boring. Oh, and I wanted to say back here, I said almost all available cards. Rick Lethenius sent me his before lunch. I didn't see it till after lunch. I didn't have time to incorporate his into the plots. And plus this plot here is 4x7. It's a nice number. With him, it makes 29. It's a prime number, and it's difficult to add into the plot. So I just gave him his own page. But that's a good opportunity to see one of these spikes I keep talking about. He had a good one at about frame 9700 or so, where you get this big jump in brightness for a very short period of time during the reappearance event, or reappearance part of the event. So that said, here's everybody's data plotted together. In this case, I plotted on the x-axis, I've done it distance from the center of the moon. That way I can make sense of where these things are in relation to the moon and the atmosphere. And then the vertical axis is just the distance normal to the direction of motion. Motion is left to right in this picture. I did not try to rotate it to the actual north up orientation that we often do, just because it'd be harder to plot if nothing else. I don't have labeled who all is who on this plot, but the big takeaway, first off, the dark inner circle, that's the surface of the moon. It's got a radius of 2,575 kilometers or so. The little gray circle outside of that is 500 kilometers farther out. Like I said, Bruno Siccardi said that about 525 is where you can first start seeing effects, and there's supposed to be an inversion layer around 500. And so I put that line on there to kind of show the extent of the atmosphere, if you will. And you can see that things kind of line up well. There's no effect until we get to that line, and then there's an effect all the way down to roughly where you get to the moon's surface. You can also notice at the top, and I'll talk about this light curve a little more in a minute, but that one at the top is Peter Ceravolo's. Like I said, he was the farthest from the center line, and he has these two very prominent spikes on either side of the event. And since that curve's out there at around 500 kilometers, that leads me to believe that he's seeing that inversion layer that's supposed to be out at that distance. It doesn't show up much in any of the other ones, but he's spent the most time out there in his viewing, and so that it really showed up. I've got a little second way I plotted. This is something I was just playing with, and there's a lot of trouble. It turned out not to come out too well, but I spent a lot of time on it, so I thought I'd include it. This is basically the same data as the previous page, but now everybody's plotted as a straight line, and it's colored by intensity. So the blue is where it's the lowest value, and the red's where it's an occulted star. You can see a lot of effects of wind and stuff in there. There's a lot of extra spikes that are obviously not part of the event. But this is, a little while ago, I was talking about how I made sure everything was round, and that's how I figured out my offset. This is the plot basically I used to do that. I just eyeballed to see that these effects were evenly spaced between the two rings, in case you were curious how I was doing that. Another thing that's kind of interesting in this picture, if you look in the left-hand side between the two circles at about 1,250 kilometers or so on the y-axis, you can see it's kind of a light blue area, but there's some darker blue stripes in there. It looks like several people got those stripes in the same spot. It turns out that was one of the best spots where I could tell, yes, people were seeing the same events. And I'm going to be showing some line plots of that in a few minutes. So, trying to go into individual effects now. First thing is just large scale refraction effects. I've got my curve and Greg Luzinga's light curve on here. And first thing you see is the bottom of it is not flat. And that's because of that big refraction effect where the star is behind the moon, but you're still seeing it because the light's bending around it. And so it doesn't give us a nice flat bottom. So we're able to see that. So at least one phenomenon we got. I'd already talked about the spikes that we could see. Oh, and incidentally, this is a 1 second running average, a moving average of the data to try to get rid of some of the high frequency stuff so you can see some of the other details. One of which is this thing that looks kind of like a central peak. I had noticed that when I first sent my data to the group. It's like, I should be too far away to see that, but it was interesting. Rick got the same thing. He got the only other person that got fairly definite spike. It's just like, could that be a central peak? Well, the answer is no. That's kind of shown in this picture. The picture on the right here is the same ground track that you saw before for this event. The one on the left is from an event that occurred in 2003. In fact, on that day, Titan occulted 2 different stars, one visible from like the tip of Africa, I believe, and then this one that was just south of the US. The gray band on the left is the ground track, which looks very much like the one that we had. I mean, it goes almost across the same parts of the US and South America with just a tiny shift. The dark gray region in the middle is where this paper that I reference here said that you could have a central flash. Could you be close enough to the center line to see it? It's actually a very narrow region. And since these are so similar, you'd expect that same region to go just around the tip of Florida. Also in this most recent event, I'm on the Texas Gulf Coast, close to Houston, so I'm way outside of that. Greg is even farther away, and nobody in between us saw spikes. One person closer to the center than me didn't see a spike. So I think we just had some unfortunate clouds. If you have enough light curves, you're always going to be able to see something that looks like real data, even if it isn't. Another interesting one was from Chris Anderson. His had the most pronounced spikes. I talk about spikes a lot, and you can really see them in this picture. Obviously, something's going on in the atmosphere. He was he's like the 3rd farthest from the center, and he was very close to where I think the edge of the moon would have been. A couple of clouds, I didn't take those out just because it really starts messing with the spikes whenever you're trying to normalize this kind of data. They didn't really seem to hurt anything. But I thought this was the most dramatic, and they really get a lot brighter. I'd kind of normalize this, 0 being the dimmest it gets, and 1 is the brightest for the main part of the event. And you see these numbers reach almost 5. So these are bright spikes. Another interesting one. This was the one farthest from the center, Peter Ceravolo again. These are the 2 spikes you can see on the previous plot. They're very symmetric about the center line. 0 on the x-axis is where I estimated the center was. Actually, the lucky star prediction is a little left of that, and the lucky star prediction is actually closer to being centered between those spikes. So I may still be off a little bit. But see those 2 big spikes, kind of a little M shape in the middle. And then which I'm assuming that since we're so close to that 500-kilometer line, I assume that's that inversion layer. Another interesting thing is far from the left, though, at around minus 500 kilometers, where we see a spike. And it looks kind of like noise, except it's like 5 or 6 data points on that. And so I'm kind of wondering if that could be really some little wave in the atmosphere, some little high density, relatively high density spot that caused some refraction out there. I really don't know, but I thought that was a very interesting point. There's a little thing around minus 250 kilometers. There's just a single point. I think that's just a little bit of a scintillation right there, or something that took out the star for a frame or a field. But this I thought was one of the most interesting light curve ball. The normalized brightness doesn't really make a lot of sense because it's hard to figure out where 0 and 1 were, but it doesn't really matter for this plot. Now, the next one is very similar. This is Bill Hanna, who is the next person closer to the center than Peter was. What's interesting, you get a little dip in the middle, which is where it started to go through the atmosphere. All the cloud stuff off to the right, you can ignore that. He was able to clean that up quite well. I wasn't as successful, and I didn't want to mess with the other spikes, like I was saying before, so I left the clouds in this one. What's interesting is there are 2 groups of spikes kind of on either side of the center line. And then there's a 3rd spike spaced about the same distance off to the left. And I realized the spacing between those 3 is very close to the spacing of these 3 from Peter Ceravolo. So my suspicion is 2 and 3 are the same as these symmetric spikes, and then 1 is the same as that spike he had off to the left, because the spacing is about right. These x-axes are very different, and the spacing looks roughly correct. So I think that they are both seeing the same phenomenon, just he's seeing just a little bit farther into the atmosphere. Another interesting thing is he has an asymmetric disappearance and reappearance. Disappearance is more gradual, reappearance is steeper. One other person saw that in his light curve, I forget who it was. In this case, since there were so many clouds, it could be cloud related, could be clouds on Titan, could be clouds on the Earth, I really don't know. Or it could be some other asymmetry in the atmosphere because we are kind of skimming the edge. And I should also point out, if 2 and 3 are really those symmetric points, they're actually centered a little bit to the right of 0, whereas Peter's were a little bit to the left. Makes me think that maybe I had the event centered just right, but there's some of those things sort of like a polar hood that are shifting things around, even though their track did not go right through where that would be. You know, it's actually off to the side somewhere. A couple more. This is where I started trying to compare people to see if everybody got the same, if anybody got the same spikes, or was it all noise? And so I picked out just 4 observers to keep it simple. 2 pairs, Johnny Barton and Dave Eisfeld were very close together. Both live close to Waco, Texas. And they got Paul Maley and Tony George who were close. And there was quite a few people close to those 2. Theirs just kind of was a clean set of data for this comparison, so I'm showing them. But the one thing and I've also plotted this differently than before. The horizontal axis is now the brightness, darkest to the left, brightest to the right. And I just shifted the 2 curves to make them closer together. That spacing means nothing. The vertical axis, though, is the height above the surface. And I left the numbers off of that. I figured I was starting to get kind of the Lucky Stars regime. I didn't want to, show their data before they have a chance to analyze it themselves. But it doesn't really matter what those heights are. You can see, though, that there are a few spikes, the largest spikes, that do line up. For the one on the left, at the disappearance, the biggest spike matches the next one down. Now you got some large spikes that are not really seeing so much of the other one. And then there's a couple of spikes lower down that seem to match up fairly well. But at least that tells me there's some data here that they're going to be able to pull out of the noise, which was encouraging. At reappearance, there's not as many. There's only 3 spikes that really look to me like they line up for sure. But there's some of the basic shapes in the data a little bit farther down where it looks like we got the same general trends in the data. So again, I'm hoping Lucky Star can do a lot with this. I took it a little bit farther for the data on the left. And what I did here is basically the same thing, but now I smoothed the data by doing a moving average back to making 1 second exposures essentially. And I've done everybody that was around, excuse me, I can drink. Right around the guys that we saw on the previous plot. The magenta and blue lines are those same curves, but now smooth. An interesting thing here is I've drawn lines through what I think are the same features, and they're actually easier to see if you turn your screen 90 degrees, but I didn't have time to change the plot. At any rate, it looks like a lot of these curves line up, especially the 6 in the middle. Mine is the curve off far left, and it's got 2 drops that seem to match up. The interesting thing is with this average data, this is the only time you really see drops, some kind of attenuation happening in the atmosphere due to like haze layers. It looks like there's at least 3 haze layers, maybe. It's a little bit hand waving because there's a lot of noise, but a lot of the features match up, at least for those 6 in the middle. I will say those lines that I drew through there should be horizontal the way I calculated this. And the fact they're not makes me think I don't have my card offset and time exactly right, but still, it's encouraging. I think Lucky Star will be able to do something with this data. So that's all the data I was going to show. Just a few considerations, sort of like lessons learned from emails and stuff that's bouncing around. First off, if we ever get a chance to do another one with an atmosphere, and these don't happen very often, the fact that you're outside the ground track, if that ground track's based on the moon, you may still be in the atmosphere. You're going to take data all the way out so you can find the extent of the atmosphere. But the bright spikes, this is one that surprised me. I didn't expect spikes to be so bright around the DNR. I very carefully adjusted my gain and exposure so that I could get no saturation. I want the brightest target possible without saturation. I'm trying to get my signal to noise up. But when those spikes occur, they go way above saturation. So they saturated. I maybe should have done something to try to improve that. I'm not really sure. I guess the next time we have one of these, maybe somebody will remember this and we can have a discussion about it. Since this is really photometry as opposed to just an occultation, calibration frames are much more important, and Lucky Star wants those. And so the best time to do that is the time of the event. My camera doesn't have a temperature sensor, so I can't take dark frames at different temperatures and try to interpolate. So it's good right after the event to take some videos of dark and flat frames. For the same reason, comparison stars are even more important. Normally, we can use those in kind of extreme cases to reduce the effects of clouds. In this case, they really need that to get accurate photometry out of the data. And finally, as a bunch of people were saying, this is a very bright object. It's better not to drop the shutter speed below the frame rate. So I was doing 60 fields a second. So I used a 60th of a second shutter. That was as low as I would go. And then I lowered the gain in my case, or you can also defocus to get it where it doesn't saturate. It also helps the signal SNR. And finally, I want to just close by saying, if you haven't done it yet, upload your videos to the Lucky Star occultation portal. I don't think it's just Lucky Star's occultation portal, but they're one of the main people that use it. It looks like there were 36 successes, but when I looked an hour or so ago, they only had 29 data sets they've received and 29 people that had signed up. So if you're one of those other 7, you might want to go to that website and try to do that. And they also, if possible, want calibration data. Even if you didn't get it at the time of the event, if you could take darks and flats and send that to them to augment your data, that would really help them. So that is what I have got. And if anybody's got any questions, I would be glad to try to answer them, but I don't promise I'll be able to. Is anybody there?
Well, thank you for a wonderful presentation. That was truly fascinating. And I want to offer congratulations to everyone who successfully observed, a number of whom are participating right now in this conference.
Oh yeah, in fact, I wanted to say when I started, I had my name on the cover sheet. Really, there should have been 40 whatever names on the cover sheet, but then I couldn't have the complete picture of Titan, so I just put everybody on the big list on the side. But really, I did like 1/42 of the work for this, so it wasn't just me.
Right, yeah. Are there any questions or comments that anyone would like to make? Just unmute and speak up. Okay, well, thanks again, Phil. And